Hello everybody and welcome to this morning's webinar organised by MDPI and the Journal Processes. Today's webinar will explore eco-friendly strategies in heterogeneous and homogeneous processes. Before we begin, I'm going to take you through a little bit about MDPI and then I'll hand over to my colleague Diana, who'll tell you a little bit about the Journal Processes. From there, I'll run you through the order of today's webinar before handing over to today's chair, Professor Eleonora Neghi. A little bit about MDPI. MDPI is a pioneer in scholarly open access publishing and has supported academic communities since 1996. Based in Basel, Switzerland, MDPI has had the mission to foster open scientific exchange in all forms across all disciplines. Our 482 diverse and open access journals, including 473 peer-reviewed journals and 9 conference journals, are supported by more than 295,000 academic experts who share our mission, values, and commitment to providing high-quality service for our authors.
Good morning, everyone. My name is Diana. I'm Journal Relations Specialist for Processes Journal. So today I want to share with you some little information about our journal. As you already see here, Processes is an international peer-reviewed open access journal on processes or systems in chemistry, biology, materials, energy, environment, food, pharmaceutical, manufacturing, automation and control, catalysis, separation, particle and applied engineering fields, published monthly by MDPI. Next, I would like to let my colleague share with you today's schedule.
So today we'll be hearing a little introduction from Professor Eleonora Neghi before moving on to a talk from Professor Andrea Porchedu and then Professor Daniele Zuccaccia. We'll then have a Q&A session where you can ask any questions and have them answered by our professors and Diana before Professor Eleonora Neghi closes the webinar. So I'll hand over to Professor Neghi and she can introduce our speakers in a little bit more depth.
Thank you very much. And good morning, everyone. It's a pleasure to welcome you to this webinar titled Eco-Friendly Strategies in Homogeneous and Heterogeneous Processes, organized by Processes. And I thanks very much Processes for this great opportunity. I'm Eleonora Neghi, and I have the honor of being the chair of this event. Today, we'll explore our cutting-edge technologies and that are driving sustainable development in the chemical science. The role of chemistry and chemists in shaping a more sustainable future has never been so vital and urgent. And for this reason, this event offers a unique opportunity to discuss some of the most innovative strategies that are transforming chemical processes towards greater sustainability. We are honored to have 2 distinguished speakers with us, whose pioneering research exemplified the spirit of innovation in this field. Our first speaker is Professor Andrea Porchedu from the University of Cagliari. His research focuses on sustainable synthesis methodologies, particular mechanochemistry, with application in medicinal chemistry and industrial synthesis. And the title of his presentation is From Ball Mills to Green Molecules, the Mechanochemical Revolution. Our second speaker is Professor Daniele Zuccaccia from the University of Udine. His research focuses on the synthesis and application of homogeneous catalysts for the sustainable and green production of chemical products. And the title of today's presentation is Sustainable Homogeneous Gold Catalyst from Neat to Green Solvent. Before we begin, I'd like to remind that we'll have a question and answer session at the end of the presentations, and I encourage you to participate actively by asking questions and sharing your valuable perspectives. Sustainability is a shared responsibility, and only through open collaboration can we have a significant impact. So thank you again for being here, And I now hand over to Professor Porceddu for his presentation.
Thank you, Eleonora, for your kind introduction. Yes, now I started to share the PowerPoint, just a few seconds to start. So today, my presentation will be focused on from ball mill to green molecules, the mechanochemical revolution. Just before to start, I want just to introduce myself. My lab, Greeting Laboratory, is seated in south of Sardinia. If I have just to use a few words to introduce the activity of my lab, we are very close to a chef where we use very cheap ingredients to produce value-added products, and we are interested in a lot of different transformation concerning, for example, oxidation, reduction processes, non-conventional electrocycle chemistry, and many others. If you open a newspaper, or also if you check in Instagram and many other sites, you can see the problem that we have around the world: pollution, plastics, waste, and also the weather changing is another big problem that we experience. And in this context, also the accidents concerning many activities, human activities, in particular for chemistry, now start to revolution, to change the approach to chemistry. Here there is a big problem. Everyone is aware of it, yet everyone acts as it doesn't exist. This is a problem. So if you go in a market, probably you decide to use not, for example, orange, so it means natural orange, but you prefer to buy fruit already peeled and packaged. So this is a big problem. So it is you are responsible of every activity, also in the research that you realize in your lab. So when I was younger, started my PhD period, so my career, in the realization of a scientist, the most important things were the yields. So you need to prepare the products in high yields, don't putting attention to the byproduct or how the process were realized. So it means if you use bad solvent like toluene, like benzene or many other, there is no problems. But today, as you told a few minutes ago, everything is changed. One of the big problems that we have is the use of solvent, because if you consider in a reaction, the solvents cover around the 80% of components, solvent is really one of the most important problems of a reaction. Of course, you can switch to alternative burning solvent, which is a part of a progress. Another problem is the use of energy. If you consider that many reactions are heated using oil bath, and in order to transfer energy, you have to heat before the oil bath, and then oil bath transfer energy. So it's not performing as a technology. So now two problems: the solvents and also the type of source of energy in order to heat your reaction. So for our opinion, but for many other, the no solvent is the best solution. So in order to realize reaction without solvents and also to transfer energy, mechanochemistry can be a solution. For this reason, we started around 10 years ago to develop this technology. What is really mechanochemistry? Mechanochemistry is a technique through which solid reagents are transformed into product by grinding, milling, or sharing, without the needs of excessive amounts of organic solvents. So starting from an experience of all periods, in order to prepare the red color that you can see here in the picture, Cellini wrote, you have to grind, vermilion is the red color, for a lot of time, perhaps for 20 years, in order to get better and more perfect products. Perhaps for that reason, I had a lot of problem to convince the students to start a PhD period in our labs. But pay attention, today everything is changed. The machine are able to realize mechanochemistry following or so you can start an experience. You put your reaction inside a machine and everything is really better. So you move from stressed mechanochemistry to very fast and also comfortable processes. Here you can see different type of mill. Another important thing is the choice of a jar. Jar can be made of different materials, and here you can see different types. Okay, so we start experience with mortar and pestle, but now using vibratory mills, you can realize up to 5 gram experience in batch. Same experience can be realized also in planetary mill, but in planetary mill, you can arrive up to 2 kilo, but in many parts of the world, several factors are able to realize the same experience in a centric mill, realizing synthesis up to 50 kilo. And more in short space, you can realize also mechanochemical experience using extruder. And here you can move from grams to tons. Okay, now I want just to show you in a video what happens inside a mill when a reaction starts. I hope to start the experience. So this is just to give you the idea of energy inside the mechanochemistry processes. And more, checking the second point, this is really important. So you have neat processes, but the part of a material really involved during the impact is really, really little. So it means it's very close to a diluted experience. Here you can see also other type of different jar of different material, for zirconia up to agate. Okay, so why mechanochemistry today is so important? As you can see from the diagram, the number of papers published in mechanochemistry increase year after years. Because of the strategies, the processes is very easy. You have only to place the jar, add the first and second or more reagent, close the jar, and start the experiment. Without putting attention, for example, to use argon or to use particular condition. This is for the most of experience that we see in our lab. Mechanochemistry started really in a night of time. So it means in 300 BC with a Theophrastus reduction of cinnabar. For 2,000 years, silence, no results, no experience. Mechanochemistry started again with Faraday, reduction of silver. Faraday start to think about the effects of pressure on photographic plates. Oswald start writing the first mechanochemistry textbook, and we have just to wait in the 1923 to see the first automatic mortar grinding. And in 2020, the UPAC defined the mechanochemistry as one of the top 10 emerging technology in chemistry. And now a lot of experience, processes, and publication are in the literature. I want just to introduce one experiment of Matthew Carey in order to understand some important things. So in chemistry, we are involved day after day to search age, to increase age, parameter, citation, number of publication, losing the knowledge. So Carey Ling was a very rich person, was a scientist, and during his transfer to another house, the holiday house, he sent 3 different packaging containing silver colloid. The color of his powder was of gold, but when the powder arrived, one of them changed the color to white. But this powder did not see light. He was packaged inside a vials, and during the transfer, the movements generate energy, mechanochemistry energy, and the color changed from of gold to white. And so, starting from this experience, perhaps start also the mechanochemistry. In order to confirm this experience, he sent 3 different samples and observed the same experience. So one of the important things is, but what is really mechanochemistry? Is something eating, close to eating, or is different? Michael Faraday observed that if you grind silver chloride in presence of zinc, you are able to get silver metals. Matthew Carey observed the similar experience grinding for 10 minutes. 10 minutes of share was able to generate silver metals. Also with mercury dichloride. But if you try to repeat the same experiment eating, you can observe only melting and sublimation of the same material. So just to show you the differences. In Bologna, the Professor Maini also repeated the experiments of Theophrastus using cinnabar ore, observing that grinding in the presence of acetic acid, really you can transform cinnabar in mercury. But in order to get the same experiments with classical approach, so Bunsen burner, or also eating, you need a lot of energy. So just to convince you about the differences about mechanochemistry and other classical technology. Moving to chemistry, so here you can see very classical Suzuki-Miyaura processes. You need to use palladium acetate. If you want to realize the same experiment using mortar and pestle, of course, the result changes too much if you are gym man or woman. And also, you can see how the frequencies, so the number of impact for time change, increasing the frequencies. So this is just to see how the machine are very important for their reproducibility, but also to increase the yields. Another important thing is the quantity or the form of energy transferred during the impact. For example, you can use a planetary ball mill at 13 Hertz. You can experience and good yields for a Mizuki-Eck reaction. It's a classical approach. But if you try to hit the same experiment in a test tube, the yields are very low. Yes, you can steer the test tube at 80 degrees, pay attention, and not at room temperature, like in a ball mill. But the yield increased, but not so much. If you want just to use an hydraulic pressure at 80 degrees, the yield don't change too much. So what is important? The number of impact inside the jar, high energy, but not the pressure. Okay, this is another experience. It's really important because you can experience a Knoenagle reaction. You can monitoring the same reaction using also Raman, and you can see how the reaction changed too much, moving from mortar and pestle to ball mill. In ball mill, after 35 minutes, you have complete conversion. In mortar and pestle, after 60 minutes, you have only 11% of conversion. So just to show you how important is the use of device. Energy, okay. Joachim Stoll also observed, for example, for homocoupling of aniline in the formation of azobenzene, that ball mill require less energy in comparison to a classic heating, microwave, and ultrasound. And the same experience was also extended to Suzuki-Miyaura, glacier reaction, and Knoenagle processes, just to convince you that the energy in mechanochemistry is really low in comparison to other technology. How is possible? If you go into a children's playgrounds, you can observe, for example, if you sit up in a merry-go-round, but you don't need too much energy to turn. So it's the same reaction, so the same experience that you can see in a planetary ball mill, just to have an idea of the low energy employed in mechanochemistry processes. Okay, now I want just to show you some experiment and stop at me when my time is concluded. Custom Ball observed, for example, a lot of differences performing variation in mechanochemistry, for example, in the CEH amidation of benzamide. Using a classical approach, you need 12 hours and 50 degrees. The same experiments reproduced in mortar and pestols require around 100 minutes, and the yields are quite the same. Lamartine in Montpellier observed that in the formation of CuNHC complexes, the yields are, sorry, just very low, 19%, and can be increased a lot when you use the mechanochemistry approach, only 8 hours to receive the product in good yields. Sorry. If you observe, one of the components of this reaction is copper. You can realize the same experiment using copper jars. Copper jar, it means jar made of copper. So you don't need to add the catalyst. You have the catalyst just present or as a balls, the balls used to realize the experiment, or in the wall of a jar. When other classical reaction is the reduction of ester using sodium borhydride in the presence of lithium chloride. Using ball mill, you can realize the same experiments that you can observe in solution in only 1 hour, maintaining the same results, just to see how easy it the process is. Another parameter is the use of solvents. Pay attention, what means the use of the solvent. The solvent should only wet the surface of particles. So you use very little amount of solvent. Just a little amount, it means microliters. One parameter is eta. So eta is the microliters of solvent versus the milligrams of reagent, solid reagent inside your jar. So knitting green, it means eta 0. The quantities of solvent can be add up to realize eta 1. Then you have slurry. More 5, you have homogeneous solution. So it means few and few microliters. So 1 or 2 drops. The advantage of a liquid-assisted grinding is to accelerate variation, to improve selectivity, to enable access to new polymorph, etc. So here just a few slides to conclude my activities. Here you can see how variation change, adding some drop of solvents. Here is a Suzuki Miura co-scrapping. In a classical experiment, so you can see the reaction was performed using dioxane, very toxic, 60%, in methanol 10%. You can observe practically complete conversion, just adding a few drops of methanol in a jar. So less than 10% in batch using classical solvent at reflux. After 99 minutes, you can see complete conversion, adding to the jar just a few drops of methanols. You can see similar results, for example, in proline catalyzed antioxidative aldol reaction. Here, in the batch, the author used the DMF, very toxic. Now, even next year will be forbidden to use. In order to realize the experiment, the author needs 5 days. But if you realize the same experiment using a mechanochemistry approach, and proline, of course, as a chiral inductor, you can see high yields, good diastereometric ratio, and also reduced time. Other experiments can be the inserting of fluorine. Fluorine is very important for API. So in a classical approach, you can see in the fluorination of 1,3-D-ketone, you need of acetonitrile. The process required 24 hours. And in order to introduce 2 atoms of fluor, okay, you need a lot of times. In only 2 hours, the same experiment can be completed. So you use time, you save energy. More, if you remove a base, you can introduce in the same time only 1 unit of fluorine, but also adding just a few drops of acetonitrile, like condition, you can improve also the ratio between mono and D. Another very important process is the Grignard. Grignard is a classical. You are involved in Grignard processes also during the classical experiment with students, perhaps. Usually you have just to use argon or nitrogen in order to avoid side products. Professor Ito in Japan, they observed, but also Kastenbaum in Germany, that it's possible to synthesize, to prepare a Grignard in jar without paying any attention. So adding magnesium in presence of air, realizing every possible Grignard processes. Also switching from magnesium to calcium, but is impossible using a classical solvent procedure because the reagent is very low soluble. You can see many details in this paper. Okay, and you can also prepare many other catalysts following a mechanochemical route, cutting the time, realizing the same experiments. Another very important experience was described by James Mack. Using alkene in the presence of nickel catalyst, using solvents, so in a classical approach, you can get a trimmer, as here. But if you try to repeat the same experiments using nickel turnings. So the balls of experiment are made by nickel. You get trammer. So you change the results. And more is very easy to purify the final products because you have only to filter to separate the balls from the good products. I have some minutes, or it's concluded my times.
Yes, if you have
just a couple of minutes. Okay.
Okay.
I want just to present a few slides, 2 slides and no more. So here I want just to show you how the result can change really, switching from one solvent to another in liquid assisted grinding. Here you can see the homocoupling of terminal alkynes. You can generate diene or trans-enene. Using cyclohexane, the ratio between diene and enene is 7 to 30. This ratio change a lot, switch to acetonitrile. So as you can see, you can realize the experiments in good yields, but also changing the results. What is important, the mechanochemistry give us the opportunity to bypass the solubility problems. So you can realize syntheses that are impossible to be realized in solution because the reagents are not soluble. And here you can see some results. Many others are now published in literature, and I can give you some data, some example if you ask. But now my time is concluded, and I want just to present one experiment, but in short time. You can realize the boring hydrogen approach not only in solution, but now also in mechanochemistry or biomechanochemistry approach, cutting the amounts of catalyst. Using ruthenium macho, we are able to realize the experiments using 0.05 mole percent at room temperature in 6 hours. Okay, we are at the end. Sorry. So thank you for your attention. And if you have questions, I'm here to reply.
Thank you, Andrea, for your great presentation. And for the question, we have a session at the end also of the second talk. And now I ask to Professor Zuccaccia to present his talk. Thank you.
Thank you, Eleonora.
So many thanks to Eleonora and to Processes staff for this invitation. And then I'm going to speak about the development of sustainable green methodologies for homogeneous gold catalysis, with the particular attention of the role of the control ion. For example, gold in recent years is frequently used for synthesis or organic synthesis. In fact, gold possesses a unique ability to activate alkynes toward nucleophilic attack. But unfortunately, most of the gold catalyzed reaction proceed under an unfriendly condition for what concerning environmental. In fact, in gold synthesis and gold catalysis, volatile organic solvent is frequently used, and also silver salt, acid additives, and in general, high catalytic loading is requested. So the idea is, or the main goal of this project is the study of the chemical synthesis mediated by gold, with the purpose of elucidating the before go to the sustainable and green production of chemical before it is necessary to study the structure and mechanistic foundation of this type of reaction. And so the scheme of the presentation is very easy. At the beginning, we study the counter-ion effect in gold catalysis, also in organic solvents, and then try to develop a sustainable green protocols for gold catalysis. So this is the general accepted mechanism in gold catalysis. An unsaturated bond in general alkynes coordinate to gold and form intermediate one, or better, the ion pair in which there is the gold coordinating to gold and the counter-ion in the outer sphere. So the intermediate one undergoes the nucleophilic attack and produces the organogold species, the intermediate two. And then in the intermediate two, the protodirectional step gives the decided product. So if you can see that both in the nucleophilic attack and during the preparation step, we are in the presence of the cationic catalytic species. So the counter-ion may significantly impact the reactivity. We can study, for example, for cyclomerization of proprazilamide. And in this case, we can see that the reaction, the reaction is well known in literature, and the protodirection step is the protodirection is the rate determining step. So in this case, the nature of the counter-ion is very important. From an MR experiment and the FT calculation, we can see that the 3-fluoroacetate is too basic. So keep far away the hydrogen and slowing down the reaction rate. Instead, in the case of the intermolecular alkoxylation of alkyne, that is the oldest application of gold catalyst, we see that intermediate coordination ability and anion basicity perform better. From key experiments, addition of the acid and tetrabutyl monosalt, we can find that in this case, the direct determining step is the attack of the methanol. So the tosylate acts as a template during the nucleophilic attack, putting the methanol in the right position and activate the methanol by a nitrogen bond with the tosylate to the hydrogen. On the other hand, too high coordination power basicity of the anion worsen the catalyst performance by preventing alkyne coordination in the case of acetate, or by forming too much free methoxide in solution, which poison the catalyst. So this is the general result about the nature of the importance of the nature of the anion in gold catalysis. The anion properties is very important, and in particular coordination ability, basicity, and proton affinity. So the anion can impact the catalytic performance. In general, the classical non-coordinating anion, like for example BF4 or BARF, this is not a good choice. Instead, intermediate coordination and basicity ability of the anion like tosylate or tiflate provide the best compromise. This is another picture in order to understand the importance of the counter-ion in all the steps. Of course, during the pre-equilibrium step, less coordinating, less basic anion is better. But during the nucleophilic attack, mild basic and coordinating anions work better because activate the methanol or other nucleophile. On the other hand, during the protodirection step, the counter-ion moves the proton from nucleophile to gold. So also in this case, the strong basic coordinating anions can be important. So with this idea of the role of counter-ion, we try to develop a sustainable green protocols in gold catalysis, taking the advantage of the counter-ion effect. And we try to obtain in the same protocols some important green metrics, okay? For example, green solvents instead of organic solvents, neat or silver-free condition, at room temperature. We can try to use recyclable catalysts, and in order to obtain, of course, green metrics as atom economy, MI factor in agreement with the principle of green metrics. This is the first application, is the study of the hydration of alkyne catalyzed by gold catalyst, and full conversion of trihexane into 3-hexanone was obtained only in the case in which the anion is intermediate in for coordination to gold and basicity toward hydrogen. And in particular, only triflate and NCF2 is able to catalyze this reaction. This on-off catalytic behavior of the gold complexes is related to the nature of the anion. So the anion is very important in this type of reaction. Then we can try to optimize. We add a phase transfer catalyst, change the loading, change the temperature, and obtain a higher tone and off for this type of the reaction. So also in this case, the counter-ion choice is a triflate, because the triflate is able to catalyze this type of reaction. Then the absence of a solvent, because we work in net condition, allowed us to easily separate the liquid product from the solid catalyst and ionic additives by distillation, thus producing high purity adduct products. In addition, we are able to recycle the catalyst up to 4 times without appreciable loss of activity by readdition of water and hexane to the solid, and then repeat the distillation. We obtain a very interesting matrix, or green matrix, for this type of reaction. The reason is the fact that triflate can easily display from the cation, and consequently the coordination of the alkyne will take place. But during the nucleophilic attack, that is the rate determining step, triflate acts as a template, holding the water molecule in the right position for the antiplanar addition and enhancing the nucleophilicity of water. This is the first application of this concept in gold catalysis. Then there are the proton transfer. The other counter-ion are not active for this type of catalysis. Why? For what concerning BF4, BARF, or other low coordinating anion, okay, the hexane can coordinate to gold, but this type of counter-ion are not able to activate water during the nucleophilic attack. On the other hand, two basic coordinating anion like TFA, in this case, the alkyne is not able to coordinate to gold, and the reaction stops. So this is a table in which there is our approach in green, and on the other side there is the common metrics using for this type of catalysis for the literature. We can see that we are able with this protocol to have a green production of hexanone for what concerning, okay, solvent free, okay, of course it's green, okay, don't use solvents like Andrea as before, say before. And then we use local loading, obtain high TOF, low temperature, and so on. Another important aspect in gold catalysis is the use of additives. In literature, the research use additives in order to increase the reactivity of gold catalysis, in order to increase the yield and reduce the time. And additives that are hydrogen bond acceptor have low gold affinity toward gold and can increase the efficiency of the gold catalyzed reaction. Instead, acid additives, of course, increase the protoneration steps. So the idea is, okay, it is possible to develop green protocols in gold catalysis, use green solvent, because green solvent possess different functional groups, acid, basic, and so green solvent can be useful for this type of reaction. Of course, we can take into account the polarity of the solvent, which is related to free ions ion pairs, that is related to the importance of the triflate. Then we can choose a green solvent taking into account hydrogen acceptor or donor functionalities present in solvents, and then the coordination of a green solvent to the gold fragments. So we can start to study several green solvents from water, but also renewable feedstock or ionic liquid, hypothetic solvents, perfluorinatic, supercritical fluids. We can see just in this slide there is a lot of functionalities that can be related to the synthesis mediated by gold. In general, we observe high conversion in green solvent respect to GOS. When green solvent was taken into account, the polarity of the solvent can be crucial. And in fact, we observe this type of trend. This is the trend of alkoxylation of alkyne. And we can see that increasing the dielectric constant, we observe an increasing of TOF. This is related to the fact that when we increase the electron constant, we move from ion pairs to free ions. So the triflate is not able to catalyze the reaction. But we can see that there is varylactone, glycerol, and also polypropylene carbonate that is out of this trend. Why? From NMR experiment and the FET calculation, we deduced that this type of solvent does not interact with the gold, so it is not coordinating to gold, but can help during the nucleophilic attack by hydrogen bond with the nucleophile, and then can promote the protoneration step. In fact, it can interact with the proton and that move from nucleophile to the gold carbon. So this is the conclusion of my talk. At the beginning, the integrative, experimental, and theoretical approach is necessary in order to understand the foundation of this type of the analysis. And we study this reaction in conventional solvents. We're focusing on the counter-ion effect. After, when the counter-ion effect is well depicted, and also other foundation, for example, protodirection step or nucleophilic attack, then we can move to try to develop sustainable green protocols in green solvents or in heat condition, depends. In this case, the rationalization of counter-ion effect and the role of the functional group present in the solvent are very important. So I think that it is the green protocols is necessary, of course, but it's also necessary the characterization of the process before starting the green approach. So this is the idea of this research. This is the idea of my talk. The sustainability is very important, but also the understanding of the fundamentals of the processes is important in order to give better results for what concerning, in this case, sustainable chemistry. Okay, I would like to thank my colleagues of the University of Perugia, and of course, my colleagues of the University of Udine, and also my colleagues of CNR and the University of Pisa, processes, and Eleonora for the introduction, for giving me the opportunity to share my results, and also you for your kind attention.
Thank you, Daniele, for your presentation. And now, if we have the question and answer session, if you have any question for our speaker, please post them in the Q&A box at the bottom of your screen. I will start with some questions for Professor Forcaddu. So you mentioned lag reactions. And do you think that can it be useful to introduce a solid auxiliary in a mechanochemistry reaction?
Yes, thanks for the question, because it permits to introduce another parameter. For example, here the problem is another. Auxiliary, it means solid auxiliary.
Yes.
This is really important when you have a liquid component. For example, you can realize an experiment in mechanochemical condition, just absorbing your liquids. So it means liquids is reagent liquid, for example, benzaldehyde or similars, in a solid component. For example, for me, one of the most important is sodium chloride, because it's a green, of course, or silica gel sometimes, or many other components, also cellulose, so components that are not able to react in the context, of course. So this is important to introduce one other element. You can realize mechanochemistry if the components are solid. So it means one component has to be solid. If you haven't, you need to use auxiliary, solid auxiliary.
Thank you very much. Thank you. And a question for Professor Zuccaccia. Your approach is very interesting for gold, but could the same approach be used also for other metals?
Oh, yes. Okay. Yes. Yes, of course, this type of approach is possible also for other metals or other reaction catalyzed by metal. I think that when not only the control ion, but also, for example, the ligand is important in coordination chemistry. But in all these aspects, it's important that the mechanism is known by the research. So in this case, when the mechanism is known, for example, also in iridium catalyzed reaction or ruthenium or palladium, when the mechanism is known, then you can move to sustainable chemistry, changing some parameters. And for example, in I don't know, for example, in palladium chemistry, it's very important to stabilize the nanoparticles or not. Depends on the catalyst, of course. And if you have an idea to what's happening during the catalysis, you can change the green approach, solvent, no solvent, or use of additives, or other. I think so. This approach is general, I think.
Thank you very much, Daniele. And I will check that we have other questions. I don't see anything. So thank you to all our attendees for your presence and valuable contributions. A special thanks to our speaker who have enriched us today with their stimulating research and presentations. And it has been a pleasure to share the session and discussion and exchange. I hope this webinar has provided you with new perspective and useful insights. Dialogue, insight for your research, for your professional activities. I think that dialogue and the exchange of ideas are essential for progress, and today's session has been a valuable opportunity to share knowledge and stimulate reflection about our research, about our work, and how to carry it on. So thank you for all your contribution and participation, and have a good day, everybody.
Thank you, Eleonora.
Thank you, Eleonora.
Thank you very
Thank
much.
you, Eleonora.
And thank you to all the speakers for your contributions today. I hope you have a lovely day.
And also you for the invite
Yes.
to be
Thank you
part
very
of
Thank you very
this.
much for attending.
Thank you. I'll end the webinar now. Hope everyone has a lovely day.
Thank you. Bye.
Thank you. Thank you.
Bye.
Bye.